Welcome, everyone. Today we're going to explore how we measure polymer molecular weight using gel permeation chromatography, or size exclusion chromatography. This isn't just an analytical lab technique. It directly impacts how real products perform in the field. From plastics and medical devices to drug delivery systems and packaging, molecular weight determines whether a material succeeds or fails. So let's understand why this measurement matters so much. Before we talk about instruments, let's talk about behavior. Molecular weight controls almost every physical property of a polymer. Strength, viscosity, processability, and stability all depend on how long the polymer chains are. Short chains move easily, which means low strength and low viscosity. Long chains tangle together, giving higher strength and thicker flow. So if we want predictable performance, we must control molecular weight, and that means we must measure it accurately. Here's a situation many manufacturing teams face. You order the same polymer from the same supplier, but suddenly, one batch performs differently. The product becomes brittle, or too viscous, or hard to mold. Chemically, nothing changed. The real culprit is often a broader molecular weight distribution. Average numbers don't tell the whole story. This is exactly where GPC becomes powerful, because it shows the full distribution, not just one value. So what exactly is GPC, or size exclusion chromatography? It's a separation technique based purely on molecular size. Not polarity, not charge, not chemical interactions, just size and solution. Think of it like a sponge with tiny pores. Small molecules enter the pores and take longer to travel. Large molecules can't enter and pass through quickly. So large chains come out first and small ones later. That separation forms the basis of molecular weight measurement. Let's follow the path of the sample through the system. First, we dissolve the polymer completely in a suitable solvent. The pump pushes this solution through a column packed with porous beads. As the polymer flows, different chain sizes separate based on how deeply they enter those pores. The detector then records when each fraction exits. In simple terms, time becomes size, and size becomes molecular weight. That's the heart of the technique. When the analysis finishes, we see a chromatogram. But this curve is more than just a peak. Each point represents thousands of polymer chains of different lengths. From this data, we calculate key parameters. Mn, the number average molecular weight. Mw, the weight average molecular weight. And PDI, the polydispersity index. If Mw and Mn are close, the polymer is uniform. If they're far apart, the batch is broad and unpredictable. This distribution tells us how consistent the material will behave in real applications. When the analysis finishes, we see a chromatogram. But this curve is more than just a peak. Each point represents thousands of polymer chains of different lengths. From this data, we calculate key parameters. Mn, the number average molecular weight. Mw, the weight average molecular weight. And PDI, the polydispersity index. If Mw and Mn are close, the polymer is uniform. If they're far apart, the batch is broad and unpredictable. This distribution tells us how consistent the material will behave in real applications. There are two main ways to calculate molecular weight: relative and absolute methods. Traditional GPC uses calibration standards like polystyrene. This works well, but assumes your polymer behaves similarly. If it doesn't, results may be slightly inaccurate. Absolute methods, like multi-angle light scattering, measure molecular weight directly. No standards needed. These methods are especially valuable in regulated industries, where higher accuracy and regulatory confidence are critical. Here, something many textbooks don't emphasize. Most GPC problems don't come from the instrument. They come from sample preparation. Incomplete dissolution creates false high molecular weight. Aggregation looks like giant polymers. Dust blocks columns. Wrong solvent changes separation behavior. So always dissolve completely. Choose the right solvent, filter carefully, and maintain your columns. Good chromatography truly starts before injection. To wrap up, remember this. GPC is not just a testing method, it's a decision-making tool. It helps you control batch consistency, predict performance, avoid processing issues, and meet regulatory requirements. When you understand molecular weight distribution, you stop guessing and start engineering. That's the difference between trial-and-error manufacturing and true polymer science. Thank you for listening, and I hope this helps you see GPC as a powerful ally in polymer analysis.